In this lesson, Pass the Proton, we should be able to identify the acid and base by looking at a reaction. We should also be able to write a dissociation equation for acids and bases. First off, a dissociation equation is just when the ions separate in aqueous solution. So, for example, when we make a salt solution, sodium chloride for instance, we actually, the particles of sodium separate from the particles of chloride. So what we have is we have NaCl breaking up into its ions Na plus Cl minus. Similar to that one, if we have magnesium nitrate, the ions separate to magnesium plus 2 aqueous ions plus NO3 minus aqueous ions. 2 of them, in fact, and you can figure that out based on the formula because you have this 2 down here, so it breaks up into 2 of those. We talked about that when we discussed balancing way back when. Now let's figure out how this applies to acids and bases. First off, we're going to talk about the Arrhenius definition. The Arrhenius definition is really the first definition of acids and bases, and what he did was Arrhenius was a very famous young scientist who went against the grain of the experienced chemists, and actually he was ridiculed at first, but later he won a Nobel Prize because of his work. An Arrhenius acid just dissociates to form H plus ions, hydrogen ions. Another way of saying hydrogen ions is using the hydronium ions. They're really the same thing. It's simpler to think of it as H plus, but it's really the same thing as H3O plus, and you may see that in the future. So, an Arrhenius acid just dissociates into H plus ions. So, if it dissolves and it forms H plus ions, it's an acid. HNO3 is another example, dissociates into H plus ions plus nitrate ions. Moving forward, Arrhenius bases, similar to acids, dissociate to form the hydroxide ion. An example of this is NaOH, dissociates to form its ions Na plus OH minus. Calcium hydroxide dissociates to form calcium 2 ions plus 2 hydroxide ions. As scientists further learned to study acids and bases, they found out more things acted like acids and bases than just things like this. So Bronsted Lowry, they studied acids and bases and their properties and found out that it's more like transfer of H plus, where acids were hydrogen ion donors and bases were hydrogen ion acceptors. So, and we can look at the reaction like this. If we looked at this reaction below, we wouldn't be able to identify it just by the Arrhenius definition. Now, everything that's in Arrhenius acid is included in Bronsted Lowry acids, but there's more things than that. So, I draw a little Venn diagram here. So if you had Bronsted Lowry, some of these would include the Arrhenius definitions. So, everything that's a Bronsted Lowry acid is also an Arrhenius, anything that's Arrhenius acid is also a Bronsted Lowry acid as well. We can think about it like H plus is like the baseball. And when the pitcher throws the ball to the catcher, the pitcher donates the ball to the catcher, so the pitcher is like the acid, and the catcher is like the base. You can remember that because the catcher is actually at home base. So how can we identify what's the acid and base? Well, first off, we identify the pairs. We look at our HNO3 and NO3 minus, and our NH3 and our NH4 plus. Those are our pairs. So if you notice that we start out at HNO3 and end up as NO3, that's because the HNO3 donated the H plus 2NH3. And you notice NH3 starts off like that and ends up as NH4 plus.
Please call extension 27601. Thank you.
So the NH3 accepted the proton. So the HNO3 is the acid. The NH3 is the base. There's actually a name for things that end up with the H+. What ends up with the H+ in the end, the catcher after the pitch, is now called the conjugate acid. And what the pitcher's left over as doesn't have the ball anymore, so we call that the conjugate base. Moving forward, let's do another example about this, and I can give you guys some steps to figure out what is what. So if we're looking at this reaction, we want to identify our acid base, conjugate acid, and conjugate base. We look at first identify our pairs again. We have CH3COO and HCH3COO. We have NH4 and NH3. So let's look at the pairs. HCH3COO is the end. It started off as CH3COO. So this clearly gained a H+. This pair right here. So this is our base. We look at the other pair, NH4 plus, and it started in NH4 plus and ended as NH3. So that's going to be our acid. So this NH4 plus lost the H+, the CH3COO gained it. And we look at our conjugate. Who has the H+ in the end? That's our conjugate acid. And NH3 is our conjugate base. So, and you can also remember, if you figure out the acid and base, the conjugates are the opposite. The last thing we're going to discuss a little bit in this one is what it means to be a strong acid or a weak acid. Now, strong acids, they totally ionize. I like to think about this as a really bad breakup, where hydrogen and chloride are together, dating, and then they break up and have a horrible fight, and they never talk to each other again. So let's say we had a hydrochloric acid solution, and each ion that I represents 0.01 moles of each ion, and I have 1 liter of solution. So there would be 10 H pluses, and 10 Cl minuses. So the H plus and Cl minus separate because it's a strong acid. I'm going to say all separate. And this would have a pH of 1 here. And we'll talk about those calculations in the next class. So moving forward, a weak acid is similar to a strong acid, but it's like the kind of amiable breakup where the couples, they were friendly, they had a friendly breakup, and they both weren't getting along, but they stayed friends in the end. So they partially ionize, but sometimes they'll talk to each other again. In fact, most of the time that's true. So in here, the H, what happens is, so if we had acetic acid, I'm going to call, instead of writing out a bunch of CH3COO minuses, I'm going to just call it X. So we have H plus and X minus. So here, some of them stay together. Most of them, in fact. We only have a couple that don't get along and separate. But most of them stay together as HX. And they're friendly. So what happens is the H plus partially separates. from acetate. In this case, I'm abbreviating acetate with X minus, like a variable, because HCH3COO minus, or excuse me, HCH3CO is a weak acid. Now, here this pH of this is equal to 5. So it's less acidic than the same concentration. Strong acid concentration. I'll abbreviate strong acid SA. So that's it for this lesson. This is pretty easy if you rely on the basic principles, and we'll move on and do this in class.